Zeeman now,
Euclid.
and Lj Mj prime. So this is Mj prime now. But Zeeman thing commutes with Jz. Jz commutes with delta H Zeeman. Jz is Lz plus Sz, and Z components in angular momentum, two identical components always commute, of course. So Jz commutes with delta H Zeeman. So this thing will vanish unless M is equal to M prime. And that's great, because you're back to the non-degenerate perturbation theory. The whole matrix, this Zeeman thing could have turned out to be complicated matrices. No, it's perfectly diagonal in this basis. There's nothing to worry about here. Except that it's still not easy to compute, as we will see. So what do we need to compute? We'll have the first order corrections due to Zeeman on the MLJMJ basis is equal, well, the Zeeman Hamiltonian had an E over 2MC, so let's put it there. E, let's put the B close to the E, 2MC. And now we have to do MLJMJ, LZ plus 2SZ, and MJ. Perfectly diagonal. And that's non-degenerate perturbation theory is going to give us all the energies we want, all the splittings we want. So basically what's going to happen, as you can see here, is that things don't mix, everything is diagonal. So these two levels are going to split, these two levels are going to split, these four levels are going to split. Everything is going to split here. The remarkable thing of this formula, and it's going to keep us busy for about 10-15 more minutes, is that this thing, this matrix element, is proportional to Mj. So the state split proportional to the M quantum number. The state with M equal 3/2 will split 3 times as much as the state with M equal 1/2. And that's not obvious here. It's a remarkable result. It's part of what's called the Widner-Eckart theorem, something that you study in graduate quantum mechanics. So we're going to see a bit of it, the beginning of it, in this computation. And it's a fairly remarkable result. So the remarkable result here, is that E1s are proportional to Mj. And that defines a linear splitting because it's linearly proportional to the magnitude of the magnetic field and divides the states nicely. So we want to understand this matrix element, and there's a little thing we can do. Notice that Lz plus 2Sz is equal to Jz plus Sc. You can take one of the Sz's and complete Jz, and you're left with that. So the matrix element MLJM, Lz plus 2Sz, MLJMJ, is equal, if you have a Jz, that gives you just something proportional to HMJ, plus MLJMJ, SZ, MLJMJ. So, okay, a little bit of a mystery maybe seems to be at least consistent here. I said this matrix element turns out to be proportional to Mj, and certainly this piece having to do with the J component here is proportional to Mj. The mystery that remains is why this matrix element would be proportional to Mj. The story begins with a statement that we will verify to some degree in the homework that is due on Wednesday, of vector operators. This operator, SC, the one-line summary is that this operator is a vector operator under angular momentum, under the total angular momentum, and as such, its matrix elements will behave like the matrix elements of Jz. So how is that true? So suppose, what does it mean to say that S is a vector operator under J? It is to say that for J, S is like a vector. And that is a complete statement that you should check whether it's true. The statement is that Ji with Sj, here this I and J run from 1 to 3, is equal to I h bar epsilon I jk sk. That is the statement that S is a vector operator. You may have seen this in a previous course, in 805, where you might have proven that X and P are vector operators for L. And here the proof is not all that difficult. In fact, it's almost obvious this is true, isn't it? Ji is Li plus Si. Li doesn't talk to Sj. But Si with Sj satisfies the algebra of angular momentum that is precisely this one. So this is almost no calculation. You will check, remind yourself that if you have a vector, that L, for L, X and P are vector operators. So for example, Li Pj is I h bar epsilon I jk pk. And this you do by calculating the commutator, but after you calculate the commutator a few times, it's better to just remember, oh, it's a vector operator. That's a good way of thinking about this. Okay, if you have vector operators, they have a very peculiar property sometimes. One that may sound a little unmotivated, but it's very useful, is the following. Suppose you form the double commutator of j squared with the vector operator s. Here you will find an identity, and to make it fun for you, I will not tell you the number that appears here, it's some number. But with some number here, this is identical to the following: Sj times j minus 1/2 j squared s plus Sj squared. Well, it's important to look at this equation even to make sure everything is in order. This is a vector equation, so it's 3 equations. So j squared, despite all this arrow, is a scalar, has no indices. It's j1 squared plus j2 squared plus j3 squared. S, on the other hand, has an arrow, and it's a vector, so you look at this equation for the third component, for the first component, for the second. So here is a vector with 3 things. Here is also a vector. It's s dot j and j. So the vector index is carried by the j here. The vector index is carried by the s here, once to the left of j squared, once to the right of j squared. Also, maybe you should notice that Sj is the same thing as Js. Not because these operators commute, but because Sx and Jx commute. Sy and Jy commute, and Sz and Jz commute. Different components would not commute, but here these ones do commute. So this is a formula you will show by computation. I don't think there's a simple way to derive this formula, but it's true and follows by computation. This formula implies a result that is quite pretty. It's sometimes called a projection lemma. So this is all we're doing is trying to compute a matrix element, and we're forced to consider a lot of structure. We're just trying to show this simple matrix element with an Sz here is proportional to Fj. This is our goal, and we're going to do that. So suppose you take that interesting equation and find its expectation value on a state that is an eigenstate of J. So suppose you take a J Mj and put this whole equation inside this, left-hand side and right-hand side, a state that is an eigenstate of J. Now that state may be an eigenstate of other operators as well. It doesn't matter. Now look at your left-hand side. It's a commutator. You have a j squared on the left, a commutator on the right, minus commutator on the left, j squared on the right. In both cases, there will be either a j squared near the bra or a j squared near the ket. Those two terms come with opposite signs. Since those are eigenstates with the same eigenvalues, that's what we're doing, an expectation value here, the left-hand side is 0. So the left-hand side contributes nothing. So left-hand side is 0 on this thing. Is 0. And let's look at the right-hand side. Is equal to j mj s dot j mj and minus. So that was the first term. Now we have to compute this thing on this jm state. Again, a j squared is either to the left or to the right. Therefore, this gives a number, which is h squared j times j plus 1. This gives the same number associated on the bra. You have 2 terms. The factor of 1/2 cancels, and you're left just with the expectation value of s, which is kind of what we wanted here. So this is minus h squared j times j plus 1, which is the expectation value of j squared, times the expectation value jmj of s on the jmj. Okay, you have this term minus that term equal to 0. So what have we learned? We have learned that this term, that we can call expectation value of S vector on a J eigenstate, is equal to the expectation value of this quantity, S dot J on the eigenstate, divided by this number, which turns out to be the expectation value of J squared on that eigenstate. This formula looks like a projection formula, in which you say the expectation value of S is the expectation value of the projection of the vector S onto the vector J. Remember, if you have, for example, projection of a vector A into a unit vector N, what is the projection of a vector A into a unit vector N? Well, the projection is A dot N times N. That's the component of A along the vector N. But if N is not a unit vector, the projection of A along B is A dot B times B over B squared. Because, in fact, the projection along a vector or along a unit vector is the same thing. It's just a projection. And here you have unit vectors. So this is the projection lemma. It's a very nice result. Pretty striking, in fact. This result is also mentioned in Griffiths. It doesn't give a derivation of this result. It's just quoted, but it's a beautiful and important result. It's conceptually interesting. It's valid for any vector operator under J. And this will answer our question, because now we can use this formula to compute the matrix element. So what do we have for our case? We have that N, L, J, Mj, Sz, N, L, J, Mj is what? Well, we have the expectation value of Jz on the state, so it's going to be h bar mj over h squared j times j plus 1. That's the denominator. And you still have here what may look like a small challenge or a big challenge. Happily, it's a small challenge. S dot L n L j mj. Here, this is called the scalar operator. This is invariant under rotations, and scalar operators are independent of mj. We got the mj dependence here. We want to claim that this expectation value is proportional to mj, and we have the result here unless there is mj dependence here. But there's no mj dependence here because, as I said, this has to do with the fact that this is a scalar operator. So let's calculate this part to finish this whole computation. How do you do that? Well, you have to remember you have j equal to L plus S. So, in here, we'll do the following. I'm sorry, I had a confusion here. S dot j is S dot j here. It's starting to look wrong. So I need the dot product of j and s. So here, I'll take L equals to j minus s, and L squared is equal to j squared plus s squared minus 2 s dot j. Here is important that s and j, s dot j and j dot s are the same. And therefore, this s dot j is 1/2 of j squared plus s squared minus L squared. So with s dot j being this, you see immediately what is this number. This is h bar mj, h squared, j times j plus 1. And now, 1/2, so I have a 1/2 here, I'll put it in front. J squared, so this is j times j plus 1. There's an h squared in addition. H squared here. J times j plus 1, s squared, which is 3/4, so it's been 1/2, minus L squared, which is minus L times L plus 1. Okay, almost there. Wow, this takes time. But we have our result. So what is the result? The matrix element, N, Lj, Mj, Lz, oops, I'll put the whole thing together, Lz plus 2sz, back to the whole matrix element. Remember, we had one piece, HMJ, and now this part. So adding the HMJ to this new part, we have HMJ, 1 plus j times j plus 1 minus L times L plus 1 plus 3/4 over 2j times j plus 1. Okay, I'm sorry, it's all here. I just copied that term, hopefully without mistakes. So we have our matrix element, and that matrix element in the top blackboard there gives us the splitting. It's probably a good time to introduce notation, and there's a notation here for this is called G sub j of L, and it's called the Lande G factor. It's a G factor in the sense that affects the energy levels as if you were modifying the magnetic moment of the particle. So this number tells you how the levels split. They split proportional to mj, all the various levels, and for the full multiplet, the multiplet is an eigenstate of j and eigenstate of L. So throughout all the states in the multiplet, this is a single number, and just you have the h and j. End result is that the weak Zeeman splitting, NLJM, is EH bar over 2mc times b times gj of L times mj. And this number is about 579 times 10 to the minus 9 eV per Gauss. It's small. So wow, it took us some effort, but here we are. We have the weak field Zeeman splitting completely computed. So B, strong field Zeeman. So what did we say we would do? We would have H0 plus E over 2mc B LZ plus 2SZ B. This would be our H0 check, I called it, plus delta H fine structure 1. And we said, what we have to do now is strong field Zeeman is more important than fine structure. So we first have to get the strong field Zeeman figured out with the bare bones hydrogen atom, what it does. And then on those states, we will do perturbation theory for fine splitting. So it is redoing fine splitting. And you say, oh my God, that's hard. We spent the whole lecture doing that. Well, second time you do things, they go a little faster. So it's not that bad. But here there's something quite remarkable. This was supposed to be your known Hamiltonian. You say, no, it's not known. I've never solved this before. On the other hand, when we had H0 plus delta H1, fine structure, we did struggle and we found those states, approximate states. Here the situation happening is surprisingly simple. And one reason for that is the following. That against perhaps your initial impression, this can be solved exactly. You don't even need perturbation theory to add this term. What? Yes, this Hamiltonian commutes with H0. Isn't that right? H0 is rotational invariant, so it commutes with any J. And certainly H0 has nothing for spin. It's a 1 matrix there. So this commutes with the Hamiltonian. So it's possible that you can diagonalize this completely. Simultaneous eigenstates of the first part and the second part, so simultaneous eigenstates from all of those. But the news is even better. Your uncoupled states, N, L, ML, MS, those were eigenstates, exact eigenstates of H0, the all good old hydrogen atom. But actually they are exact eigenstates of LZ and exact eigenstates of SZ, so they're exact eigenstates of the Zeeman Hamiltonian. So these states are it. These are the exact states of H0 hat. These are exact eigenstates of H0 check. I'm sorry, it was not hat. With eigenenergies as follows. No mystery, the eigenenergies, they're very simple. The eigenenergies are E, N, L, M, L, M, S. Exact are E, N, 0. The ones that the hydrogen atom has that don't depend on any of these other things. Plus EB over 2MC. EH bar B over 2MC. ML plus 2MS. So this deserves perfectly the name of known Hamiltonian. That was not the case for weak Zeeman. In weak Zeeman we had this one, and that was the approximately known Hamiltonian, to which we added the weak